Hello, curious minds. Have you ever wondered why nuclear reactions release such enormous energy, even when only tiny amounts of matter are involved? Well, here's a mind-boggling thought. In nuclear reactions, a tiny bit of mass can transform into a huge amount of energy, thanks to one of the most famous equations in physics, Einstein's mass-energy equivalence. You might have heard the formula E equals mc squared, where E is energy, m is mass, and c is the speed of light in vacuum, approximately 3 times 10 to the 8 meters per second. This means that even a small mass m, when multiplied by the speed of light squared, which is a gigantic number, gives a huge energy output. So in nuclear processes, what really happens is that some mass difference, called delta m, disappears and reappears as energy, denoted E. This energy doesn't just vanish into thin air, it shows up as the kinetic energy of particles flying away or as radiation that sips out from the reaction. The incredible thing is that because nuclear forces bind protons and neutrons tightly, the very high binding energy per nucleon makes nuclear reactions extremely energy efficient. This is why nuclear power plants and even the sun produce such massive amounts of energy from changes that look very small in mass. Let's talk about what holds a nucleus together using the idea of binding energy. Binding energy, or BE, is the energy needed to tear a nucleus apart into its individual protons and neutrons. Think of it like the glue strength inside the nucleus. The higher this energy per nucleon, which is the total binding energy divided by the number of nucleons, the more stable the nucleus is. If we plot this binding energy per nucleon against the mass number A, we get an interesting curve with a clear peak around iron, where A is about 56. That peak means iron has the most tightly bound and stable nucleus. So when nuclear reactions happen, like fission or fusion, the energy released corresponds to moving the nucleus toward this peak, that is, toward a higher binding energy per nucleon and greater stability. This explains why both breaking very heavy nuclei and fusing very light nuclei release energy. They both move nuclei closer to iron's sweet spot of stability. If you picture the graph, the x-axis is mass number A and the y-axis is binding energy per nucleon, with the peak right there at iron showing maximum stability. Now, let's explore nuclear fission, the process that powers many nuclear reactors and, unfortunately, atomic bombs too. Nuclear fission happens when a heavy nucleus, like uranium-235, splits into two lighter nuclei. This splitting releases a huge amount of energy because the combined mass of the products is slightly less than the original mass. This mass difference is known as the mass defect. For example, one typical fission reaction starts with uranium-235 absorbing a neutron, and it splits into barium-144, krypton-89, plus 3 neutrons and energy, which we call Q. You can think of Q as the energy treasure chest unlocked by this reaction. Now, those 3 neutrons are like tiny messengers that can go on to hit other uranium nuclei, triggering more fissions. This is what we call a chain reaction. Imagine a neat diagram showing an incoming neutron colliding with a uranium nucleus, which then breaks apart into 2 new nuclei, with 3 more neutrons flying off to continue the cycle. Chain reactions can be powerful friends or dangerous foes, depending on whether we control them. In nuclear reactors, chain reactions are carefully moderated using moderators and control rods. Moderators, such as graphite or heavy water, slow down the neutrons, making them more likely to cause further fission. Control rods can absorb excess neutrons to keep the reaction steady, ensuring stable, controlled energy output for electricity generation. On the flip side, uncontrolled chain reactions are what happen in atomic bombs, where neutron numbers multiply rapidly without restraint, releasing a massive burst of energy explosively. To put numbers in perspective, The average number of neutrons produced per fission is about 2.5, but reactors sustain the reaction on just one neutron to maintain control. Picture the block diagram of a nuclear reactor showing fuel rods where fission happens, the moderator surrounding them, control rods sliding in and out to regulate neutrons, and a coolant system removing heat. This system keeps the nuclear fire burning safely without blowing up. Switching gears, fusion is the exact opposite of fission. It's nuclear energy from joining light nuclei instead of splitting heavy ones. Fusion typically involves isotopes of hydrogen like deuterium, which has one proton and one neutron, and tritium, with one proton and two neutrons, combining to form a helium-4 nucleus, a neutron, and releasing about 17.6 million electron volts of energy, or 17.6 MeV for short. Fusion packs more energy per nucleon than fission, making it even more powerful by weight. But there's a catch. Fusion requires incredibly high temperatures, over 10 million Kelvin, to overcome the electrostatic repulsion between positively charged nuclei. At these extreme temperatures, thermal motion is so fast that nuclei can slam together and fuse. This is exactly what powers the stars, including our Sun, through intense gravitational confinement that keeps the plasma hot and dense. Imagine a schematic showing deuterium and tritium nuclei merging to create helium, a neutron, and a flash of energy as output. Let's put some numbers into this amazing energy conversion by calculating the energy output from uranium-235 fission. Given accurate mass values of the reactants and products, we find the mass defect delta M by subtracting the total mass of products from reactants. Then we plug this mass difference into Einstein's equation, E equals delta M times C squared, where delta M is in atomic mass units, or U conveniently, one atomic mass unit corresponds to 931.5 million electron volts divided by C squared, so we convert mass directly into energy. For uranium-235 fission, the mass defect is about 0.21 U, and multiplying 0.21 U by 931.5 MeV per U gives approximately 200 MeV of energy released per fission event. To grasp the scale, the total energy released by fission of just 1 gram of uranium-235 is roughly 8.2 times 10 to the 10th joules, enormous power packed into a tiny mass. Visualize a graph showing energy increasing sharply with the number of fissions, or imagine overlaying the numerical calculation to confirm these values. Here's a neat example to calculate fusion energy released when deuterium and tritium combine. Given the masses, deuterium equals 2.0141 U, tritium 3.0160 U, helium-4 4.0026 U, and neutron 1.0087 U, we find the energy released, denoted Q. The formula is Q equals open bracket the sum of initial masses minus the sum of final masses close bracket times 931.5 MeV per U. Substituting the values, Q equals open bracket 2.0141 plus 3.0160 minus the sum of 4.0026 and 1.0087 close bracket times 931.5, which simplifies to 17.6 MeV. This matches the known fusion energy from this reaction perfectly and demonstrates why fusion is such an efficient energy source, especially in stars where millions of these reactions happen every second. To wrap up our fascinating journey through nuclear energy, remember that Einstein's mass energy equivalence, E equals delta M times C squared, is the foundation of everything we've discussed. Whether it's uranium-235 absorbing a neutron to produce barium-144, krypton-89, 3 neutrons, and energy, or light nuclei like deuterium and tritium fusing into helium, a neutron, and releasing 17.6 MeV, both fission and fusion release energy by moving toward higher nuclear stability, as explained by the binding energy per nucleon curve. Fission reactions typically release around 200 MeV per event, while fusion packs even more energy per unit mass. Nuclear reactors carefully control chain reactions using moderators and control rods to provide steady power, whereas atomic bombs unleash uncontrolled fission for massive explosions. Fusion on Earth remains a challenging goal, requiring extremely high temperatures and plasma containment, but it mimics the Sun's energy source. Both fission and fusion harness tiny mass defects to unlock vast energy, proving how energy and matter are two sides of the same cosmic coin. That is it for today's concept. Physics is fun when you can laugh and learn. See you in the next session.